we got accepted. That quite a long time. I mean, it's my first work in Slum. It's my first work collaborating with Zhao, I think.
Do you want to start?
Shall I?
Yeah, maybe you want to start. It's recorded already, I think.
Yep. Okay.
Yeah, but maybe like people
Okay.
are joining, so.
All right, cool. So thanks a lot for coming to today's reading group. And first of all, I should say thank you to all for all your interest in our work about ParallaxBA and linear Slum. I just talking about the ParallaxBA is a quite old work from me. I think we've invented in early 2010, I think. Then we submit the our conference version to ICRA that year and published in 2011. And we tried to make it in the journal version a bit later. So it's published in 2004, I think. Right, and yeah, so it is a reading group. So I try to make the methods or algorithms as detailed as possible. Some of them are not very detailed in my previous talks, if you heard, and some of them are not detailed even in the paper. Okay, and I should say when I try to prepare for this slides, and it's recall me a lot of very interesting things when I first doing research, actual research, and first doing research in Slum. And as I mentioned, the ParallaxBA is my first work in Slum, and also it's my first work collaborating with Zhao. And we start from ParallaxBA, then we work out a lot of other interesting works together a bit later. All right, so for the ParallaxBA, we first gave a brief introduction about what is Slum, what is monocular Slum, as what we what Zhao talked in last week. Then I will briefly introduce what is the parallax angle feature parameterization in monocular Slum, and then we have a theoretical analysis on different properties of different feature parameterizations. It will be very interesting. And then after that, we've introduced like how to use parallax angle parameterization to formulate the Bonner adjustment problem. And then we have some simulation and experimental results I'm going to show you. All right, so Slum, as Zhao introduced in last week. So Slum is the problems that the robot can build a map of the environment and use the map to localize itself simultaneously at the same time, right? And monocular Slum is the Slum problem that the only sensor on board the robot is a single camera. And we suppose that the camera can move arbitrarily in the 3D environment, and there's no odometry information. For example, if we put the camera on an electrical car or like autonomous car, and then when the car drives and get a sequence of, images, and you use the sequence of images to build the 3D environment as the map, and at the same time calculate the trajectory of the car. Or similarly, if you put the camera on the UAV, then when the UAV flies, it got a sequence of images on the ground, and then you use the ground to calculate the trajectories or the poses of the cameras on the UAV, and also the reconstruction of the ground surface, and also use both of them together with the sequence of images. You can we call it mosaic or fuse all the images together as a orthogonal image. Right. So those are the introduction about what is Slum and what is monocle Slum. And I mean, for Slum, I think Sheldon has make it quite clear in the last talk. Then for the ParallaxBA, for the parallax angle parameterization, is mainly about monocle Slum, which means your sensor is a camera instead of a laser or something else. Then which means it's a bearing only sensor, which means you can only observe a direction from a single image. Then it is a bit different from what we have in the normal, like a range and bearing. I mean, for example, the laser SLAM algorithm, because the observations are different. And from the observations, then it is, because it's bearing only, then it has different properties or different informations you can get from observations, and also different properties of the algorithm. So that is why we have this parallax angle parameterization. Right, so first, let's talk a little bit in details about what information we can get from the multiple views or from the monocle SLAM, and what kind of like traditional or state-of-art feature parameterizations that can be used in the monocle SLAM. So first, as I mentioned before, monocle SLAM, which only use cameras, it is a bearing only. It's kind of like a bearing only SLAM, because from one single frame, one single image, you can only observe a direction of that feature. So which means, suppose there's a feature here, so you can see my laser pointer, right? So suppose there's a feature here, then you have a camera here, right? So suppose you have a projection, which is a UV point on the image. Then from the camera center to the UV point, you can only know this 3D feature is on this ray. But from a single view, you can't observe the depth. Sheldon, is that okay if I make it in this kind of details? Because I'm thinking this is a reading group instead of like a talk, right?
Yeah, I think you can ask others, right? What's their opinion?
So others, is that okay if I'm making it in these details, or if you think that is like quite obvious, I don't need to talk about that?
I think it's good. It's better this
Okay,
way.
cool. All right, cool, thanks. I'll keep going. All right, so then the depth information is from the multiple views. So for example, if the camera moves from here to here, then it has a parallax between the two observations. Then the depth information is from this parallax. So which means if you move the camera, it causes a parallax, then you know the depth information, right? And what we always commonly used for presenting the 3D feature in the environment is XYZ. We just simply use the XYZ location of the feature to present the features in the 3D space. All right, and if the parallax is large enough, then using XYZ to present the feature works well. But let me show you another case. If a feature is a bit far away from the camera, for example, if you're walking at night, you see the moon or see a star, then you walk for 10 minutes and you see the moon or star. It's like still at the same point in the sky, right? So this is similar. So for example, if a feature is a bit far away from the camera, then which means you move a similar distance of the camera, and then it will result in a very, very small parallax. That is a far away feature. We don't know the feature is far away, but I mean, we can get it roughly from the parallax, right? So if the feature is far away from the camera, then when the camera moves, it causes very little parallax. And in this case, using XYZ is very, very inaccurate. Can anyone tell me why? Can anyone tell me why?
I guess it's noise because the parallax is really small and signal to noise ratio is really low.
Yes, that's right. That's right. For example, in this case, right? So if you have a similar level of noise comparing to this one, right? But it will cause a very large error on this depth direction. That is the reason. That is the reason why XYZ in this case is not accurate. It will cause a large error on the depth direction. And imagine this case is quite normal in the real case, especially when you perform Slum outside in outdoor environment. It is quite common. You have a lot of features which is far away, then it causes issues. I'll show you a bit later, but I mean, this is the reason why initially using XYZ cannot work quite well in monocle Slum, and also that is the reason why you cannot directly use Gauss-Newton to solve Bonner adjustment problem by using XYZ to present features. All right, then in this, so because this is the common issue in monocle Slum, then people present or proposed a new feature parameterization. It's called inverse depth parameterization in the monocle Slum. That is a very, very good, very good paper. I think I've read that paper more than 50 times, definitely. So, and also I implement it by myself in both Bonner adjustments and also in EKF Slum. So if you're interested, please have a look at the paper. I'm not going to make it very detailed in that parameterization, but in short, in this case, if the feature is quite far away, which means a little error on the observation will cause a large error on the depth. But how about if we use the inverse of the depth to parameterize the feature, right? So if you have a very large error on the depth, then it will be a very small one on the inverse of the depth. Right, so that is the, I think that is the initial purpose about why they're using inverse depth. And I should say that inverse depth works quite well in dealing with the far away features. And also it works quite well in most of the real cases. But let's see another scenario. In this scenario, the camera is moving towards the feature, right? And in this case, we don't have any information about the depth. Is that right? So because the camera is moving towards the feature, and we don't have any information on the depth. But in this case, we know the parallax is 0. It's still 0, right? But we don't know exactly the information about the depth. So in this case, from our experience, in this case, the inverse depth is not accurate anymore. So we found a lot of issues in this case by using the inverse depth, especially in the Bonner adjustment problem. All right, so let's give some summary. So as we know, from the multiple images, the depth information is from the parallax angle, right? And we cannot always get the depth information. But we can always get the parallax information. For example, in this case, in the last two cases, the parallax angles are close to 0 or even equal to 0, right? But in this case, we have the depth information, but with quite large error. And in the last case, we don't have any depth information. But for all the three cases, we have the information about parallax, accurate information about parallax. So that's our question. So why we are using XYZ or inverse depth to parameterize the 3D feature in the monocle Slum, and why we are not using the parallax angle as a parameter to present the 3D feature in the environment. So that is why we propose this parallax angle feature parameterization. It is quite straightforward. I'm trying to make it clear and quick. So as we know, when the feature is first observed by a camera, and we only know the direction from the camera to the feature, but we don't know the depth, right? So in this case, the feature has 2 degrees of freedom. So in this case, we use 2 angles to present together with the camera center, the camera location as the main anchor to present the feature when it's first observed. So in this case, when the feature is first observed on the image, so we parameterize it by using phi and theta, which presenting the direction of this observation vector, and together with the camera center as the main anchor. All right, so for the feature observed at first time, we use 2 angles together with the camera center as the main anchor to present that feature. And when the feature is observed at second time or more, then we're adding 1 angle more comparing to the feature observed first time. That is the parallax angle omega. So this angle is the parallax angle between the observation vector from the main anchor Tm and the observation vector from the associated anchor Ta. And here we also add an associated anchor, which is the camera center or camera location of this observation vector. All right. So in the so for the features which are observed 2 times or more, that is a full 3D feature. Then we use three angles, phi theta, which presents the direction of the observation vector at the main anchor, and also the omega, which is the parallax angle between the 2 observation vectors at both the associated anchor, the main anchor and associated anchor, right? And together with 2 anchors to represent the 3D point, right? So just repeat it again. So if the feature is observed at the first time, we use 2 angles together with 1 anchor to present the feature. And if the feature is observed 2 times or more, then we use 3 angles together with 2 anchors to present a 3D feature.
So the first 2 parameters are like rotation and the first 2 parameters are rotation and elevation regarding to first camera.
Yes. So this is, we call it azimuth and elevation angles, which means, so suppose there is a 3D vector in the 3D space, then without considering its length, it only has 2 degrees of freedom, right? So we can use 2 angles to present the direction of that observation vector relative to the or from the main anchor.
Right. So once one second camera is introduced, these 2 parameters are still like these 2 parameters still regarding to first camera frame.
Yes, that's right.
Okay.
The first, yes, that's why we have 2. That's a good question. So that's why we have like a main anchor and an associated anchor. So those 2 angles representing the direction of the observation vector is with respect to the main anchor, even it is observed like 2 times or more. All right, and the associated anchor defines the second observation vector, which from the 2 observation vectors we can get the parallax angle.
Right, and the anchor here is referring to like XYZ pixel in the picture.
It's XYZ position of the camera pose. We can say the camera translation or camera center.
Okay, yeah.
It's like a camera. It's like a camera, a part of camera pose. So for camera pose, you have rotation and translation, right? And the translation is also the camera position, right? And the anchors are the camera translations.
Yeah, got it.
Okay, great. So that's a very good point. Thanks. And let me ask you a question. In most of the cases, the features are not observed only twice in molecular slime, right? So how about if a feature is observed, like let's say like 5 or 10 times from different images? Then how can we choose? How can we choose the main anchor and associated anchors? This initially is a question to me and also to Shadung, and I think initially I think it's very easy to deal with it, and that's why we propose a strategy for choosing the anchors. So when the feature is observed the first time, it initialized as 2 angles with main anchor. And when the feature is observed the second time, then we initialize the parallax angle as well, and together to define the second. I mean the camera pose, the camera translation or the camera center is observed the second time as the associated anchor. And when the feature is observed the third time, for example, then we have a strategy to compare the parallax angles. So if the parallax angle is larger than the previous one, then we choose the parallax angle. We choose the largest parallax angle, and we defined the main anchor and associated anchor with respect to the largest parallax angle. And also here we gave a threshold. We gave a threshold to avoid like keep changing the anchors, and we only gave like 0.02 radians as a threshold. So which means if the current parallax angle we initialized is larger than 0.02 radians, then we are not changing it anymore. And it works quite well, I should say, even with a very small threshold. So even the threshold is very small, but it works quite well. But later, I think we try to use some larger, we try to test on some larger parallax by using this strategy about changing anchors. And sometimes, most of the time, it seems like similar. But sometimes, if you change the anchors which are which are closing the large loop, for example, if feature 1 is observed at post 1, post 2, and post 100, then you choose the anchors as post 1 and post 100. Then sometimes it increases a little bit on the convergence. But I mean, we didn't. We can't get a very clear conclusion on that, but we can say is we just use a very small threshold on this changing anchor strategy, but then it works quite well. So which means we don't need to think about too much about, we always keep getting a very large parallax when choosing the anchors, but it can work quite well. So initially we are thinking it will be a big issue on that, but in the real case, it doesn't. Yeah, I saw. I think I hear some questions.
Oh yeah, so like it's basically whenever trying to localize the current features, we only consider 2 cameras actually, just like 2 every time, just 2.
No. It's like it's a parametrization. So which means in the Slum, we use all the observations from all the images,
Yeah.
but you only need 2 anchors and 3 angles to present a feature. So which means suppose a feature is observed by camera image 1, 2, and 3, for example, then you can use camera 1 and 2 as the anchor. Then you can use camera 1 and 3 as the anchor. You can use camera 2 and 3 as the anchor. So you have the flexibility of choosing the anchors among those 3. And doesn't affect too much if the, in this case, we're choosing the thresholds as 0.02 radians.
Right, I see.
Okay, cool. Yeah, that's a good question. All right, so if you have any questions, just stop me and ask, because I mean, it's good to understand it quite well, and then we can keep moving. All right, okay, so if all good, we try to, after we have this parameterization and we try to do some analysis on the properties, we want to see some, we want to get some similar conclusions from the theoretical analysis on different parameterizations, because when we use different parameterizations in the monocular Slum, we find the singularity issues, and we found the shadow points. We found it quite hard, quite like slow to converge, but we found it has very good property on the convergence property on the boundary adjustment using parallax angle. So we want to have some theoretical analysis on different parameterizations in different topics. So in this analysis, because the monocular Slum case is quite complicated, so it is very hard to do some analysis on the 3D case. So in this case, we just simplify the problem by using a 2D bearing only case, and we only have 1 feature, and we have like 2 images to observe it, or 2 robots to observe it. So we have 2 robot poses, and we have 2 observations, sit 1 and sit 2, which are the I think there's, sorry, let me stop it. I think there is a question from the chat. For most of the case, I mean, that's a very good question. So for a normal case about parallax, it is smaller than pi, right? And we can choose the maximum one. But in our case, I gave a threshold at 0.02. So which means if a parallax is larger than 0.02, then I'm not changing the anchors anymore. So which means it works quite well. So which means we don't have to choose the maximum parallax angle in this case.
Yeah, I think on the other side, all the parallax angle are less than pi, right? There's no case
yes.
for parallax angle to be greater.
Yes, yes, yes. Yeah, I'm waiting for some other questions in this case. I prepared 1 slide, so I want to say it at last. Yeah.
Hi, Liang. I have one question. When you say change the angle, do you mean change the main angle for this feature?
Main and associate, you can change both.
Okay.
You can change both.
So when we observe one feature, is there only one main angle for this feature, right?
Yes, only one main anchor and only one associate anchor.
Oh, I mean, for example, if we observe one feature for 3 times, and we choose one angle and 2 associated angle for this in the multiple observation, right?
That's a very good point. That's a very good point. Let me make it clear. So for each of the feature, we only use 3 angles together with 2 anchors to present it. So which means no matter how many times the features are observed, the feature is observed, then you only choose one main anchor and one associated anchor to present that feature. So in your case, if the feature is observed by image 1, 2, and 3, you can choose image 1 or camera 1 and 2 as the main and associated anchor, or you can choose camera 2 or 3, or you can choose camera 1 and 3. But you only choose 2 of them.
Yeah, and we pick the maximum. Like,
no. This is what I said about threshold. This is something I want to say that. So we changed the anchor, but if the current parallax angle is larger than 0.02 radians, I'm not going to change it anymore. So it's not always changing the maximum one.
It's thresholding at 0.02.
Yes. So this is something I want to say. So I think that's a very good point. This is something I want to say. So initially, I'm thinking we need to always change to the largest one, or always the larger one, right? But in the real case, the 0.02 radians is a very small angle. It's a very small angle, and we apply that threshold, and after that, it doesn't affect anything on the Bonner adjustment result or multiple Slum result. That is very interesting, which means we don't require a very large parallax, which we choose when we choose the main and associated anchor.
When the parallax is really large, is that affecting the algorithm convergence?
Yeah, this is what I say. It's not. It's not. It's not. That's why we put 0.02. 0.02 is very, very small, right? It's very, very small angle, and it doesn't affect the convergence of the Bonner adjustment.
So normally, the larger the parallax angle, the better. But in reality, it doesn't need to be too large, right?
Yes. I think that's a very, 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 very good conclusion on this. Thanks, Jordan. All good? Keep going?
Yeah.
Okay, cool.
Thank you.
There's another question, I think.
Yeah.
In the chat.
To the main motivation of using parallax. Yeah, so the main reason of using parallax is what we, I think what I mentioned at the beginning. So let me.
Yeah, I think the Fred asking, this looks like contradicting to the way we are using parallax, right? So like the small angle is good already.
Yeah.
Probably what we can say is we want the parallax to be not too close to 0, but as long as it's slightly different from 0, that's good enough.
Yeah. And I think another way of explaining it is the parallax angle parameterization is very close to the measurement space. So I have some like theoretical proofs about the relationships between the error on the projection and the error on the parallax. So they are on the same scale. They are very close to the measurement space. Then, which means you don't have to give a very large parallax. But instead, if it is not as small, then it doesn't affect the result. That's some intuitive like explanation on this.
Like another, like what motivates you to use parallax for parametrization?
Sorry?
What motivates you for using parallax for parametrization?
Yeah, this is what I mentioned at the beginning.
So for the distance, just for the depth issue?
Yes, it's about like a good, as what we mentioned here. So we want to have a better parameterization, which can deal with different kind of features in monocular Slum nicely.
Yeah.
This is the main like motivation, and we observed a lot of like issues when we use XYZ or inverse steps to parameterize the feature in the monocular Slum. So that's why we want to propose the parallax angle one.
Yeah. Got it.
Yeah, cool. Okay, so yeah, let's go.
Liang, may I make a quick point here, just for probably for the new people that is for the people that are new to Slum. So parametrization, so feature parametrizations and even robot parametrizations have been it's been a big research area. Has been a big research area in the Slum. So because different parametrizations will make things more Gaussian or more linear, things like that. So it's this work goes in that field where finding the best parametrization to get the best optimization or the best estimation of the robot and the map. Yeah, sorry, Liang.
Just... Thanks, Teresa. Thanks a lot. Yeah, so let's go back to the analysis. So we observe a lot of different properties or issues of using different parameterizations in monocle Slum. Then we want to have a theoretical analysis on it and to prove that really happens. And as I mentioned, it is a bit hard to analyze on the 3D case. So we simplified it into a 2D case, which we only have one feature and observed. Observed from two cameras, and we only, for each of the position, we only have one varying angle observation, right? In this case, and the first we analyze the singularity of the information matrix, and in this case, from the simulation we have, then we try to calculate the information matrix from the Jacobian, definitely, which is the partial derivative of the objective of the observation function with respect to the to different Fisher parameterizations. Then we compare the XYZ. We use steps. Instead of XYZ to do the analysis on the XYZ, and inverse steps and the parallax angle. As we can see for the XYZ case, so this is the information matrix, and this is the partial derivative of the observation function with respect to the parameter d, depth d. And in this case, we can see when the phi is equal to 0, when the phi is equal to 0, then this term is equal to 0, then which means it is singular. The information matrix is singular, right? And when the depth d is close to is very large, is close to infinity, it's very large, then in this case, this term is close to 0, then the information matrix will have very large condition number, right? So that's reflect those two cases back into the figure. So when the phi is equal to 0, so which means the camera is moving towards the feature, right? So in this case, we don't have depth information, and definitely it's the information matrix will be singular, right? And another case is when depth is very large, then which means the feature is very far away. Then in this case, the information matrix is will have large condition number, so which means it's close to singular. So that reflects the case that we really have in the monocular Slum problem. All right, then that explains why the singularity issues happened when the depth is quite far away, or when the camera is moving towards the feature. It happens. The singularity issues happens for the XYZ parameterization, right? And for the inverse steps, we also write the information matrix, and from that we can find again when the phi angle is equal to 0, so which means the camera is moving towards the feature, then it has singularity. So it's the information matrix will be singular. And when the rho, which is the inverse steps, is very large, then the information matrix will have large condition number, is close to singular. So that is also the case that happened in the real monocular Slum problem. All right, and I should say in the real scenario, the inverse of the depth will in the real case will not be very large, because the very large inverse steps means the very close the feature like to the camera. But in the real case, it will not. It normally will not happen. But I should say we are using optimization or estimation method to solve the problem. So in one of the step or in one of the each iteration of the optimization, if the inverse steps at that time is very large, then it will get singular issues, and then it will not get a very good result after that. All right. And for the parallax angle parameterization that we can see in this case, I mean, it's a simplified case, then the information metrics will always be positive definite. But that is the analysis on the singularity of information metrics for different parameterizations. Then we've done another thing. We've done the analysis on the objective function of different parameterizations in the boundary adjustment problem, right? And we first calculate the partial derivatives of the objective function with respect to different parameters, depth d, inverse depth rho, and parallax angle, right? And we want to see apart from the actual local minimum, the global minimum, or actual result, actual solution, are there any other points that cause the derivative of the objective function equal to 0 or close to 0? All right. So in the XYZ case, if we start from here, and again, the objective function will be equal to 0 if the phi angle is 0, so which means the camera is moving towards the feature, and the objective function will the derivative of the objective function is close to 0 if the steps is very large. So this is similar as what we had before. And also for the inverse steps, when the phi is equal to 0, then the camera is moving towards the feature. Then the derivative of objective function will be equal to 0. Then if the inverse depth rho is very large, then which means the derivative of object function will be close to 0. And in the parallax angle parameterization, we only have one solution when the derivative of objective function is equal to 0. All right. So what's the meaning about like if the derivative of the object function is close to 0 or is equal to 0? Then let me show you some figures. Then it will be quite intuitive to have the ideas about what they mean, right? So this is a 1D figure on a simulation in boundary adjustment by using different feature parameterizations, and the x-axis are the values of the parameters, steps, inverse steps, and the parallax angle, and the y direction is the objective function. All right, as we can see in the XYZ case, it definitely has a global minimum there. That's the right solution. But if the depth is a little bit large or a little bit small, then the objective function change to flat. So which means if at any of the iteration, if the depth is here, then it will be really, really hard to get into the right solution. All right, and add that here. So that is also the issue we have for the XYZ boundary adjustment, because even you use LM to solve the XYZ boundary adjustment, then you can see it will converge very, very slow, but without any stop. So which means at that time, at that step, the depths of some of the features are at this point. We call the shadow point. We'll show the 2D and 3D one a bit later. So which means it will change along this direction and very, very large, maybe very large because it's flat, but it's very, very hard to get into the right one. All right, and for the inverse steps, it's similar. So we have a global minimum there, but when the inverse steps is large, then it gets to a flat area, which is very hard. We call it shadow point, and it's very hard to get into the right position. And for the parallax angle, and it seems like it's very smooth and nice, right? But it's a simulation, but I mean very smooth and nice for the shape of the objective function. And then showing you a 1D, 2D, 3D case of the boundary adjustment by using the real data set. So this is an example by using the Malaga like parking 6L data set, I remember. So if we can see the boundary adjustment using XYZ, then when it converts, we choose some of the problem features, and we can see from the 1D, so for the 1D curve, then the feature, the change of the change of the feature depth will not affect the change of the objective function, right? So it's a flat area. And also, if you see the 2D contour, the 2D contour one, so which means this is the x-axis is the depth, the y-axis is some other parameters, and you can see the point is somewhere at a shadow point, some kind of like a valley. So which means from this direction, it is the minimum. It is the minimum point, but at this direction, it is flat. Every angle, so every value is the same. So that is the reason it caused its singularity, and also it caused the very long convergence using LM, because it's always like seeking points on this direction, because it's flat, but it will never get back into the global minimum. And for the inverse steps, we also found a lot of like features have the same issue. But for the ParallaxBA, we randomly choose some of the features that never have that kind of like shadow point issues, and we can see if we draw the objective functions, and we can see the feature is in the minimum point. So that is the analysis on the objective function between different parametrizations. And then we also have analysis on the initialization of the features. So in this case, we try to calculate the depths, the inverse depths, and the parallax angle from the observations. And we calculate the partial derivatives of the depths, inverse depths, and parallax angle with respect to the observation error. And we can see like how large the initialization error will be. Then for the XYZ case, and we can see from, where is it? From here and here. So if omega, so which is the parallax, if omega is close to 0, so which means if there's low parallax, then it will have very large error when you calculate the initial guess of the depth feature, right? And for the inverse steps, as we can see from here for the denominator, so a small or near 0 parallax omega will not cause any issue. But if omega plus phi is close to 0, then it will have very large inverse depth error. And this case, if you remember the figure, in this case, if omega plus phi is close to 0, so which means the camera is moving towards the feature. So which means if the camera is close to moving towards the feature, then it will have very large error on the inverse steps. And for the parallax angle, it always has the same scale as the observation error. And as we can say, if there's no outliers, right? So the observation error are very, very small normally, then which means the error on the parallax angle are always very small. All right, so that is about the some of the theoretical analysis on the simplified case for different parametrizations, and it's confirmed what we found in the real experiments in the molecular slime. All right, so I don't think I have too much time. So I have lots of details on the boundary adjustment part, and also very interesting about like how to calculate the reprojections from the parallax angle parameterization. It's very interesting, but I mean a bit complicated. But I mean I'll try to skip that and showing you some results. And we made the parallax angle on the we make the parallax angle on the boundary adjustment because the boundary adjustment is the gold standard for the molecular SLAM, and it is particularly suitable for boundary adjustment because if you remember, so for each of the feature, the 3D feature, it used three angles together with 2 camera centers as the parameters, right? But in boundary adjustment, all the camera centers, all the camera poses are in the state vector. So which means we didn't add any extra parameters in the state, and it's resulting in that we didn't resulting in that there's no additional computational cost, and we only use 3 angles to present the features because the camera centers are part of the camera pose, which are optimized to get together in the boundary adjustment. And if I have time later, I can show you the details. But I mean, we initially submitted this paper to ICAR, is nicely smoothly got accepted. But when we try to write a journal version and submit it to TRO, then we found a lot of questions, and the main question is about I didn't make a real-time implementation. So we spent nearly a year to make a real-time implementation. Most of work is done by one of my classmates. We have same supplier when I was in Peking University, and we worked together on that. And finally, after a year, so we think we make a reasonably good real-time implementation on the boundary adjustment by using the parallax angle parameterization. We called it the ParallaxBA. And for our implementation, it is for one iteration, it is much faster than SBA and a little bit faster than SSBA and very close to G2O, but with much less iteration. So totally the total time will be like much shorter than the others, and also has the better convergence because it avoids the singularity of the information matrix and avoid the shadow points of the object function, and also it always guarantees the accurate initial guess of the feature location for the boundary adjustment. So we've released that code to the Open Slum. So if you're interested, you can download it and have a try. And we have some simulation and real experiments. For simulation, we've done a lot of simulation, but I would just want to show this one because this one is simulating about the camera is moving towards the feature, but we have some error on it. It's not 100%. It's not 100% like moving towards the feature, but I mean it's simulating that case with some noise. And as we can see for inverse steps and XYZ, it always have like singularity issues. Even use LM, then it has a lot more like iterations. And for the ParallaxBA, then it's only couple of iterations, and we can use Gauss-Newton. So I can't promise that for any of the case, the boundary adjustment, the ParallaxBA can converge using Gauss-Newton. But for a relatively small problem, for example, sliding window or a small like case with couple of tens of images, then it can be, most of the cases can be guaranteed it can be converged by using the Gauss-Newton. So this is what we can't imagine before, because when I first work on the molecular SLAM, especially the boundary adjustment, then it never it never get use of Gauss-Newton. It's always like LM. And then we also have some experiments on the Malaga datasets, and I don't want to show this. I want to show some examples, the example like problem features we found in this dataset. So after it converged, then we found some features, problem features with very large error. As we can see, the feature, the problem feature for the inverse depth is more or less about like the camera is moving towards it. So in this case, it's moving forward, and also that is another feature. So if you can see, there's a red one there. As we can see, when the camera turns, when the vehicle turns, it's some kind of like still like towards that feature. So those are the two examples of the problem features in the inverse steps. And we also have some results by using different data sets. So this is photogrammetric village data set. We have 90 images, then we have 300 3D features and 800 projections. Then for each iteration is only, for us, it's only 0.6 seconds. And totally we use like couple of iterations, and the total time is around 5 seconds for that. And you can see it has the best convergence property comparing to the others. And here's another like data set. We have like around 1.2 million 3D features and 3 million projections and around 500 images. Then it takes about 2.7 seconds per iteration, and totally is about like 50 seconds to converge, something like that. And for the others, because of the singularity issues or shadow point issues, it take a lot of iterations to make it converge. All right, so there are some other results. Here is a result about photogrammetry. We use like 33 million 3D features, around 75 projections, 75 million projections, and we make a reconstruction of the terrain surface. All right, so I think that's more or less about it. And we have the paper published in the IJR, and we have the source code released. All right, thank you very much. And any questions? Shudong, sorry, I don't even have time to finish everything for the parallax. I can do it a bit later about or next week about the linear slab one.
Yeah, we leave it to next week. But I better have some questions.
Yeah. Any questions?
Like, what makes you come out with this idea of parallax? Like, it's really optimal. Like, it honestly, it's really looks like very superior algorithm. Like that's very efficient and optimal. But it's like, how come it just comes with it?
Okay, that's a very good question. I think Shudong can also answer that question as well. But I mean, from my point of view, first is we think the before we have this idea about parallax angle parameterization, the best one is the inverse steps one. But we still think inverse steps parameterization is not perfect in theoretically and also in the real case. Because even, I mean, using inverse of depth, sometimes you can't have the depth information, right? So I think this is the question Shudong asked to me, because Shudong said the inverse depth is not perfect. We're trying to get a better one comparing to that. So that is the main purpose. And also in the real case, we find some issues. In the real scenario, find some issues for both the XYZ and the inverse depth. So we want to have a better one, and we spent a lot of time to like invent it. I mean, we tried different things about how to present it, and also I think the discussion is quite important. So at that time, I think I didn't like think about other things, the things other than these parameterization things, and I keep thinking, and also discussion is very important. Every day, I think I discuss with Shudong like more than 2 or 3 times when I have some ideas, and during the discussion, I think we will create some kind of new things. At least we can find some like better ideas we can try. And after a lot of discussions, we suddenly, it seems it's quite interesting. So after a discussion, one day after discussion with Shedong, I got back to my place and keep like thinking about that, and Shedong get back to home, and at that night we both have this idea about like using the parallax angle to present it. So I should say this idea is coming from the discussion together with Shedong. So it's not only my idea, I believe. So it's a joint idea between me and Shedong. So discussion is something I want to recommend to you and to all the other like researchers. It's very important.
Yeah. Okay.
Yeah, I think I need to leave, but I just want to add one thing. For the inverse steps parameterization, the first two angles are the same as this parallax angle parameterization. So only difference is the parallax angle.
Yeah. And two anchors. So inverse steps only use one anchor.
Yeah.
Thanks for them.
Yeah, I have to leave. Sorry.
No worries. See. Any other questions? All right. So if no questions, Teresa, shall we like conclude this session?
Yeah, thanks. Yeah, for sure. Thanks, Liang.
No, right,
it was an awesome talk. I suddenly turned off my camera. I was sitting. Damn it.
Thanks.
Anyway, thanks everybody. Thanks, Liang. So you're gonna continue next week, right?
Yeah, maybe I continue next week for the leader
Awesome.
one. If you
Great.
all right. See you guys. Thanks a lot. Thanks a lot for your interest in this program.
Thanks, Liang. See ya.
Thank you. See you.